Welcome to Calm Space Studio, a place where you can let the day fall away and simply rest. Tonight we're going to explore the quiet story of water, from its birth in ancient stars to the rivers and oceans that shape our world. So settle in, get comfortable, and let your mind drift gently through one of nature's most beautiful journeys. We'll take a calm, detailed look at water's full story, from its creation in the hearts of stars to the moment it fell as rain on a young earth. We'll see why its shape gives it such unusual powers, how it built the rivers and glaciers that shaped our world, and why every cell in your body depends on it. This is a slow journey through one of nature's most fascinating puzzles. So, get comfortable, let your mind settle and think about this. Long before there were oceans or clouds, before Earth itself existed, where did the very first drop of water come from? More than 13 billion years ago, the universe was young, hot, and mostly empty. Out of that vast, glowing beginning came the simplest element of all, hydrogen. These were the first atoms to form after the Big Bang. Single protons with a light electron circling them, drifting through the cooling darkness. For a long time, hydrogen was almost all there was. No stars, no planets, no chemistry as we know it. Just a silent sea of invisible gas waiting for gravity to do something interesting. When the first stars finally ignited, they began to change everything. Inside their cores, hydrogen atoms were crushed and fused into helium, releasing light that filled the early cosmos. Over time, as these stars aged and died, their furnaces started building heavier elements. Oxygen, the other half of the recipe for water, was one of them. It didn't exist until stars made it, and when those stars exploded as supernova, they scattered their oxygen into space like cosmic confetti. Each blast seeded the universe with the raw ingredients for future chemistry, including the first possible droplets of water. In the quiet clouds that followed, the real story began. Not with oceans or storms, but with individual molecules finding each other in the dark. Within these cold molecular clouds, the temperature could drop to only a few dozen degrees above absolute zero. Here, atoms crept together slowly, bumping into dust grains and other atoms. Hydrogen, being plentiful and restless, often found itself in triads, tiny clusters of three atoms known as H3+. These molecular ions were like matchmakers of the universe, transferring protons and sparking reactions wherever they went. When hydrogen ions met free oxygen atoms or simple oxygen molecules, they formed hydroxyl radicals, short-lived combinations of one oxygen and one hydrogen atom. Those radicals didn't last long before latching onto another hydrogen, and just like that, the first molecules of water appeared. They were fragile, fleeting things, sometimes destroyed by radiation, sometimes frozen onto dust grains. But they were real. The same chemistry that happens in interstellar space today was already underway more than 12 billion years ago. Over millions of years, these dust grains coated with icy mantles clumped together under gravity, forming denser and denser regions that would eventually collapse into new stars. Around each forming star spun a thin disk of gas and dust, a kind of cosmic workshop where the elements could mix and react. In those protoplanetary disks, water existed in both vapor and ice form, creating a subtle boundary scientists now call the snow line. Inside that line, close to the newborn star, it was too warm for ice to survive. Beyond it, temperatures dropped low enough for water to freeze onto grains. Those frozen particles became the building blocks for comets, asteroids, and eventually the icy outer planets. Even at this early stage, water was everywhere. a quiet passenger on the long road to planet formation. When these icy bodies collided and merged, they carried their stored water with them, embedding it into larger worlds. Some of that water evaporated into vapor. Some stayed locked in minerals deep underground. The chemistry that began in starlit clouds was now shaping solid ground. When the Earth formed about 4 billion years ago, it wasn't the blue world we know today. It was a violent molten sphere under constant bombardment from leftover debris. For a long time, the planet's surface was too hot for liquid water to exist. Any that tried to settle would have boiled, away instantly. But as the crust thickened and volcanic activity began to release gases, the early atmosphere slowly filled with steam, carbon dioxide, and nitrogen. Water was trapped inside the rocks of the mantle and escaped through volcanic vents and cracks, adding to the growing blanket of vapor above. At the same time, countless comets and water-rich asteroids struck the surface. Each impact delivered more frozen cargo, possibly enough to fill the young oceans many times over. Scientists still debate the exact proportions, whether most of our water came from inside the planet or from space. But the evidence suggests a mixture of both. One clue lies in the ratio of deuterium, a heavy isotope of hydrogen, to normal hydrogen. This deuterium to hydrogen ratio acts like a chemical fingerprint. The ratio found in Earth's oceans closely matches that of certain types of asteroids, suggesting that much of our water may have arrived as rock-bound ice rather than cometary frost. Once the planet cooled enough, the change was almost instant. Clouds thickened and for the first time rain began to fall. Imagine the sound of it. Drops hissing on hot rock, steam rising from a scorched surface, rivers forming where moments before there had been only fire. It might have rained for centuries without pause, water condensing from the sky and returning as vapor again and again until the surface was finally cool enough to let the first pools remain. Those pools merged into basins, and the basins deepened into oceans. Steam that had once filled the air condensed into seas that now covered most of the planet. The Earth's face began to glisten for the first time, reflecting starlight and the pale glow of a newborn sun. In a sense, the planet found its shimmer, the thin, shining film of liquid that would one day cradle life. By the time that first sunlight scattered through the atmosphere, Earth's water had already travelled an extraordinary journey, from hydrogen created in the first seconds of the universe to oxygen forged in the hearts of dying stars, to molecules assembled in dark clouds, and finally to the oceans that lap against our shores today. Every glass of water, every raindrop and snowflake carries atoms that were once part of ancient stars. So the next time you see rain streaking down a window, it's worth remembering that it began billions of years ago in a place without light or warmth. That what you're seeing is the universe itself, condensed into something you can hold. Somewhere deep in the past, a single droplet met the surface of a young Earth for the very first time. It struck hot rock, hissed into steam, and vanished. But in that brief moment, the planet began to cool, and the story of everything that followed quietly began. If you could shrink yourself down to the size of an atom and look at a molecule of water up close, you might be surprised by its shape. It's not symmetrical, not neatly balanced, and certainly not what most people imagine when they think of something so ordinary. Each water molecule is made of one oxygen atom joined to two hydrogens. But instead of sitting in a straight line, the hydrogens bend away from each other, forming an angle of about 104 degrees. It's a small detail, but this bent geometry is the reason water behaves like nothing else in the universe. Oxygen is the heavyweight in this trio. It has 8 protons in its nucleus, which gives it a stronger pull on electrons than the lightweight hydrogen atoms beside it. When they form bonds, oxygen doesn't share equally. It hogs the electrons just a little, creating an uneven spread of charge. The oxygen end becomes slightly negative and the hydrogens become slightly positive. Scientists write this as delta negative on the oxygen and delta positive on the hydrogens. That unevenness makes water a polar molecule, one with a positive side and a negative side like a microscopic magnet. This polarity might sound like a technical curiosity, but it's the foundation for almost every one of water's strange tricks. Because each molecule has 2 tiny positive tips and 1 negative side, it can attract others in every direction. Opposite charges pull together, and in liquid water, these attractions form and break billions of times every second. It's this constant dance of weak electrical bonds that makes water so cohesive, meaning it tends to stick to itself. If the molecule were perfectly straight and symmetrical, those charges would cancel out and the substance we know as water would lose most of its personality. Water's dipole moment, a measure of how unevenly the charge is distributed, means it also reacts dramatically to electric fields. In strong fields, water molecules twist and align like compass needles, their positive sides turning toward the negative pole and vice versa. This behavior helps explain why water is such a powerful solvent and why it can interact so readily with ions and charged particles. Even in an ordinary glass of water, the molecules are constantly orienting, spinning and flipping in response to subtle fields created by dissolved salts and minerals. Polarity also explains something you can actually see. When you place a small droplet of water on a clean surface, it doesn't flatten completely. It forms a bead. That little dome shape is the visible signature of cohesion, the inward pull of water molecules clinging to each other more strongly than they cling to the air. The surface acts like a stretched elastic film, giving rise to what we call surface tension. It's why a water strider can skate across a pond without sinking, and why a carefully placed paperclip can float on water despite being made of metal. At a molecular level, each surface molecule feels a stronger pull toward its neighbors below than toward the empty air above, creating a tight, self-supporting skin. But water isn't just cohesive, it's also adhesive, meaning it's drawn to other materials as well. When a droplet lands on something like glass, the positive hydrogen ends are attracted to the negatively charged oxygen atoms in the glass surface. The result is a subtle competition between cohesion and adhesion. If cohesion wins, the water forms beads that sit high and round like on wax leaves. If adhesion wins, the water spreads out in a thin film, clinging tightly to the surface. You can see this tug of war at work every time rain lands on a car bonnet or slides down a window pane. This delicate balance also creates one of water's most useful behaviors, capillary action. In narrow spaces, like the thin tubes inside plants, adhesion pulls water upward along the walls, while cohesion keeps the column of liquid connected. Together, they allow water to climb against gravity, feeding leaves that may sit tens of meters above the ground. The same process lets paper towels soak up spills or draws ink through the nib of a pen. It's one of those quiet physical miracles that seems obvious until you think about what's really happening. Liquid climbing on its own, powered only by the geometry of its molecules. You can see similar effects almost anywhere if you look closely enough. When water clings to the side of a glass, it forms a small upward curve called a meniscus. In a test tube, this meniscus is concave. The edges rise slightly higher than the center because the water sticks to the glass walls. Mercury, by contrast, forms a convex meniscus that bulges upward because its atoms prefer each other's company to the surface they sit on. In something as simple as that curve, you can see the entire philosophy of water, a constant negotiation between attraction, balance, and movement. If you were to compare a droplet of water on different materials, you'd see how the shape changes with the strength of adhesion. On wax or oily surfaces, the droplet stays almost perfectly spherical, as if the molecules are huddling together to avoid contact. On glass or fabric, it flattens out, spreading wide as the hydrogens reach toward oxygen atoms in the material below. And on the delicate surface of a leaf, you get a mix of both. A round droplet that sticks firmly enough to stay in place, yet rolls away when the leaf trembles. Each shape, each curve is a fingerprint of molecular geometry made visible at human scale. This same structure also helps explain why water interacts so readily with ions, charged particles dissolved in solution. The slightly positive hydrogens surround negatively charged ions like chloride, while the slightly negative oxygen end points toward positive ions like sodium. The result is a kind of microscopic embrace. Each ion becomes wrapped in a shell of oriented water molecules. This process, called hydration, is what allows salts to dissolve and biological systems to function. Without the bent polar shape of water, those ions would stay clumped together, and most of chemistry from digestion to photosynthesis simply wouldn't work. Even the smooth surfaces we take for granted depend on this geometry. The thin film of water that coats everything from soil particles to skin cells acts as a lubricant because of those polar attractions. Molecules slide over one another easily but never quite let go. This is why water can feel both slippery and sticky depending on the surface. That same behavior helps regulate friction inside living organisms, allowing cells to move and muscles to glide. All of this stems from the simple fact that water's electrons don't sit neatly in the middle. Its lopsided design gives it direction, character, and the ability to form fleeting connections that hold entire systems together. Every droplet that hangs from a leaf tip, every bead that rolls across wax, every tiny ripple that breaks and reforms on a pond, all of it happens because of that small persistent angle of 104.5 degrees. It's easy to overlook just how strange that is. Many molecules around water's size are gases at room temperature: ammonia, methane, hydrogen sulfide. But water's polarity and its network of bonds hold it together as a liquid. Its shape lets it defy the trends that govern most other substances. Without that asymmetry, there would be no cohesion, no surface tension, no rivers or cells or clouds. When you next see a drop of water slide down a window or balance on a leaf, you're really watching billions of polar molecules in perfect coordination, each one tiny and bent, yet all of them working together to create something smooth, continuous, and alive. From the smallest bead on glass to the largest ocean wave, every curve begins with that same subtle angle, the crooked geometry that made the world fluid. If water's shape gives it personality, hydrogen bonds give it structure, an invisible framework that turns chaos into coherence. They are delicate connections, but without them, liquid water simply wouldn't exist. A hydrogen bond forms when the slightly positive hydrogen atom of one molecule is attracted to the slightly negative oxygen atom of another. It isn't a full chemical bond, more a fleeting attraction, electrostatic, directional, and temporary. But billions of these brief connections give water its strength. Inside every droplet, this network is alive with motion. Each water molecule can form up to 4 hydrogen bonds at once, but they don't last. In less than a trillionth of a second, one breaks and another forms elsewhere. The result is a constantly shifting pattern of molecular connections, a fluid architecture that rearranges itself billions of times a second. Scientists sometimes call it a liquid with a memory for order. It remembers how to be structured even as it melts, ripples, and flows. That endless motion gives water its texture: smooth, continuous, but never static. Compared with most small molecules, water flows oddly slowly. The same bonds that link its molecules also hold them back, adding a quiet viscosity. They resist being pulled apart, yet yield just enough to move gracefully. This is why water pours with such even rhythm. It stretches without snapping, flexes without scattering into chaos. Hydrogen bonds are the quiet reason a pond can carry a walking insect, or why a leaf holds a perfect droplet after rain. At the liquid surface, molecules have neighbours beside them, but none above, so their bonds pull inward and sideways, tightening the layer into a thin elastic skin. Surface tension, born from those bonds, gives water its distinctive resilience. To a water strider, that skin might as well be glass. Its legs dent the surface, dimpling the hydrogen-bonded layer without breaking it. From above, the insect's footprints are tiny ovals of tension, ripples in a field of invisible energy. Beneath that same principle lies the difference between a surface that beads with moisture and one that absorbs it. When water meets glass, the molecules find plenty of sites to bond with. The oxygen atoms of the glass attract the hydrogens of the water, spreading the droplet thin. On wax or oil, there's nothing to grab, so the water retreats into itself, forming neat spheres. Cohesion keeps the droplet intact. Adhesion determines where it stays. Together they make the world's smallest tug-of-war, shaping how rain gathers, drips, and slides. In narrow spaces, hydrogen bonds pull off an even stranger trick: capillary rise. When a thin tube touches water, the molecules at the edge cling to the walls while still holding tightly to one another. That combined pull draws the entire column upward, seemingly against gravity. In trees, this effect is magnified through millions of tiny tubes in the xylem. As water evaporates from the leaves, more is drawn up to replace it, rising meter by meter through nothing more than molecular cooperation. No engines, no pumps, just hydrogen bonds and the quiet persistence of physics. Those same bonds also turn water into a remarkable caretaker for other substances. When an ionic compound like salt dissolves, its charged particles are immediately surrounded by clouds of water molecules. The positive hydrogens turn toward chloride ions. The negative oxygen faces sodium. These hydration shells act like bodyguards, preventing the ions from reuniting. Without them, salt would stay solid, and most biological chemistry would come to a standstill. The same process happens inside you. Every ion in your bloodstream, sodium, potassium, calcium, is wrapped in a halo of water molecules, each held in place by those fleeting bonds. They keep nutrients moving, maintain the delicate balance of your cells, and help transmit electrical signals that let your muscles contract and your heart beat. Water isn't just a solvent here. It's an active participant in the choreography of life. Even in the stillness of a glass, water never truly rests. At any moment, countless bonds are forming and breaking, creating tiny fluctuations that ripple through the liquid. These rearrangements scatter light, giving clean water its faint blue tint. Under the right conditions, the same microstructure creates shimmering thin films, the kind you see on bubbles or the surface of freshly poured water. What looks calm from afar is actually an unending rearrangement at the molecular scale. The beauty of hydrogen bonding is in its impermanence. Each bond is weaker than a typical covalent bond by a factor of 20. But that weakness is exactly what allows flexibility. Ice owes its structure to hydrogen bonds frozen in place, but liquid water owes its fluidity to their transience. They hold together just long enough to cooperate, then let go to reform elsewhere. This balance between order and chaos gives water its dual identity, stable yet adaptable, strong yet endlessly soft. Nature uses this property in extraordinary ways. Inside living cells, hydrogen bonds in and around water guide the folding of proteins into the precise shapes needed for life. They stabilize DNA, holding its two strands together until it's time to separate and copy genetic information. Even enzymes rely on water's hydrogen bonding ability to position molecules perfectly before a reaction. Every beat of your heart, every flicker of thought depends on these quiet electrostatic whispers linking molecule to molecule. Beyond biology, the same physics shapes the natural world. The curve of a droplet on a leaf, the shimmer of morning dew, the gentle pull of sap up a redwood, all are manifestations of hydrogen bonding in action. It's a force so small that it can't be seen directly, yet so universal that it dictates the behavior of oceans and clouds alike. The wonder lies in how temporary these bonds are. In less than a blink of an eye, the arrangement of molecules in a lake, a cloud, or even a teacup has completely changed. Yet the water's identity stays the same. It's an ever-renewing network that never loses its coherence. Each molecule plays its part for a moment, then hands the connection onto another, keeping the chain unbroken. Every droplet, every ripple, every patch of mist is made of these fleeting bridges. They are the quiet architects of liquid life, invisible, transient, and endlessly rebuilding. Without them, water would spill apart into vapor or freeze into brittleness. With them, it flows, clings, climbs, and carries the chemistry of the world. Hydrogen bonds are proof that strength doesn't always come from permanence. Sometimes it comes from the ability to change quickly, to connect and release in perfect rhythm. They are the reason a puddle reflects the sky, a river holds its shape, and a living cell can exist at all, tiny momentary threads holding together the fabric of the liquid world. When most substances freeze, they shrink and sink. Their molecules slow down, move closer together, and pack into denser, heavier forms. Water, of course, does the opposite. It refuses to follow the rules. When it freezes, it expands, becoming lighter, larger, and able to float upon itself. It's one of the strangest quirks in chemistry, and one of the most important reasons life on Earth exists at all. The reason lies in the structure water adopts as it turns to ice. In its liquid form, the molecules are constantly jostling and rearranging, their hydrogen bonds forming and breaking 1 trillion times a second. But as the temperature drops, that restless movement slows. The molecules start to settle into a fixed pattern, aligning themselves through hydrogen bonds into a precise geometry, a hexagonal crystal lattice. This lattice looks like a honeycomb made of molecules, neat rings of 6 connected by delicate bridges of hydrogen bonds. It's beautifully ordered, but surprisingly spacious. Each molecule holds its neighbours at arm's length, leaving tiny pockets of empty space within the pattern. This open framework makes ice less dense than liquid water. Instead of packing tightly, the molecules spread apart just enough to give solid water more volume for the same mass, which is why it floats. If you've ever watched ice cubes bob in a glass or seen a frozen pond with liquid water beneath it, you're witnessing this quiet defiance of physics. In almost every other material, the solid phase sinks. But because ice is less dense, it forms a floating lid instead. That simple fact has saved countless ecosystems from freezing solid. the magic doesn't stop at the surface. Liquid water reaches its maximum density at around 4 degrees Celsius, just a few degrees above freezing. That means when water cools, the densest layer sinks to the bottom while the lighter, colder layers stay on top. In winter, as the air chills the surface, water near the top cools to 4 degrees and sinks, mixing the lake until the entire volume reaches that temperature. Any further cooling creates water that's less dense, so it stays near the surface, eventually freezing into ice. This layering creates a remarkable refuge. Beneath the ice, the water remains liquid, insulated by the frozen sheet above. Fish and aquatic plants survive the coldest months in this stable environment, safe from the freezing air. Even in the harshest winters, the world under the ice continues quietly, shielded by a crystalline ceiling that lets light through but keeps the warmth in. Without that density anomaly, every pond and lake would freeze solid from the bottom up each year, leaving nothing alive when spring returned. Water's relationship with temperature and pressure is unusually complex, something chemists describe with a phase diagram. In simple terms, it's a map showing which form water takes under different conditions. At low temperatures and low pressures, ice dominates. As temperature rises, it melts into liquid. And at still higher temperatures or lower pressures, it becomes vapor. But ice itself isn't just one kind of solid. Under different combinations of pressure and temperature, it can form at least 19 distinct crystalline structures known as polymorphs. The one we're familiar with, the type that forms snowflakes, frost and frozen lakes, is called Ice 1H for hexagonal. Its molecules are arranged in that open six-sided network we see in snow crystals. Under higher pressures, though, the structure changes dramatically. Ice 2, Ice 3, and beyond all have denser arrangements where molecules are squeezed into tighter patterns. Some of these exotic forms exist naturally deep inside icy moons and planets, where crushing pressure transforms water into something more like rock than crystal. Even on Earth, you can glimpse the influence of ice's expansion in the slow, patient force it exerts on the world around it. When water seeps into cracks in rock and freezes, the growing ice pushes outward. It might only expand by about 9%, but that's enough to wedge stones apart and carve landscapes over millennia. Mountains crumble grain by grain, boulders fracture and cliffs erode, all because frozen water gently insists on taking up a little extra space. This process, known as freeze-thaw weathering, is one of nature's quiet engines of change. It works in silence season after season, breaking down mountains to make soil and valleys where forests will one day grow. The same expansion also gives rise to frost heave in soil, when moisture trapped underground freezes and swells, lifting the earth and shifting roads, rocks, and roots. It's an inconvenience to engineers, but a gift to ecology. That subtle stirring of the ground mixes minerals, aerates the soil, and prepares it for the next cycle of growth. Ice may seem still, but it never stops reshaping the world. On a smaller scale, the hexagonal symmetry of ice gives snowflakes their iconic beauty. Each crystal begins as a speck of dust or pollen around which water vapor freezes, forming a six-sided seed. As it tumbles through changing layers of air, the molecule-by-molecule architecture of the lattice builds outward in branching, intricate patterns. No two flakes are truly identical because the path each one takes through the sky is unique, yet all share the same foundation, the hexagonal bond geometry that water chooses every time it slows and solidifies. In glaciers, the structure becomes a record of history. As snow accumulates and compresses, it traps pockets of air between ice crystals. Over thousands of years, those tiny bubbles become sealed time capsules. Scientists can drill deep into ancient ice sheets and extract cores that preserve samples of the atmosphere from long before humans existed. The faint blue glow of ancient glacial ice isn't just beautiful, it's a window into vanished climates, each bubble a whisper from a colder, quieter past. Even the sound of cracking ice carries traces of its structure. When a frozen lake groans or splits in winter, what you're hearing is the sudden readjustment of millions of crystal bonds. Temperature changes cause the lattice to contract or expand unevenly, creating echoes that travel across the surface. Beneath the noise, hydrogen bonds are stretching and sliding back into alignment, the same network that once floated snowflakes now resonating like a frozen drum. For all its apparent fragility, ice is one of the strongest materials in nature. A block of pure cold ice can bear immense weight before breaking thanks to the strength of its hydrogen-bonded lattice. Yet, it remains light enough to drift, forming an ever-shifting balance between rigidity and buoyancy. It's a substance that manages to be both solid and gentle, a paradox of physics shaped entirely by geometry. Water's decision to expand when it freezes might seem like a minor technical detail, but without it, Earth would be unrecognizable. Rivers would freeze from the bottom up, oceans would become blocks of solid ice, and the seasonal rhythm of life would halt. The same delicate structure that traps air in glaciers also traps warmth beneath the winter surface, preserving the living pulse of the planet. Every frozen pond, every icicle, every drifting flow is built from that same repeating hexagonal pattern, a molecular architecture that stretches across continents. In the depths of ancient ice, the air bubbles glint faintly blue, suspended in perfect stillness. Each one holds a trace of breath from an age long gone, a record of warmth and cold preserved by the quiet generosity of water's most improbable trick, a solid that floats. Water doesn't just quench thirst or shape landscapes. It quietly governs the temperature of almost everything around us. It's the reason coastal towns feel mild while deserts swing from blistering heat to freezing nights. It's why your body can stay near the same temperature whether you're sitting in snow or sunlight. Among all known liquids, water is one of the best at storing and releasing heat, making it the planet's thermal guardian. To understand why, it helps to think about how hard it is to warm water up. Every substance has what's called a specific heat capacity, the amount of energy required to raise its temperature. For water, that number is unusually high. It takes more heat to warm a cup of water by 1 degree than it does for almost any other common material. The reason lies in the same invisible hydrogen bonds that hold its molecules together. Before the temperature can rise, much of the added energy goes into bending, stretching, and breaking those tiny bonds. Only when enough are disrupted do the molecules begin to move faster, and the water actually gets warmer. This is why a beach can feel scorching while the sea beside it remains comfortably cool. Sand heats quickly because it stores little energy. Water heats slowly because it absorbs so much. And at night, when the air cools, the process reverses. The land gives up its heat rapidly, but the ocean releases it gradually, keeping coastal air mild long after sunset. It's a quiet exchange that shapes weather, winds, and even the survival of entire ecosystems. The same property works closer to home. Imagine stirring a pot of soup on the stove. The longer it simmers, the more evenly its temperature spreads. That's because water distributes heat remarkably well. The molecules are in constant motion, bumping into each other and sharing energy evenly throughout the liquid. This efficient balancing act is what prevents most of your dinner from burning, while a small corner boils over. In a way, water behaves like a natural thermostat. It resists sudden changes and spreads warmth wherever it flows. But there's more to water's relationship with heat than just how much it can hold. There are also the hidden thresholds called latent heats, the energy needed to change water's state without changing its temperature. When ice melts, for example, it absorbs a large amount of heat simply to loosen its rigid lattice. Yet during the entire process, the temperature remains at 0 degrees until every last crystal has turned liquid. That absorbed energy is stored invisibly in the water itself, ready to be released again when it freezes. An even greater amount of energy is required to turn liquid water into vapor. To evaporate, each molecule must break free from its neighbors completely. The hydrogen bonds that make water cohesive now become obstacles, demanding energy to escape. The result is that water can absorb tremendous amounts of heat as it evaporates, and this is precisely why sweating cools the human body. As sweat evaporates from the skin, it draws away heat energy, leaving the surface cooler. It's the same process that keeps plants from overheating when moisture evaporates from their leaves. The flip side happens during condensation, when water vapor in the air cools and returns to liquid form on a window, a leaf, or your skin after a hot shower. It releases the energy it once borrowed. That gentle warmth you feel from mist or a steamy bathroom isn't your imagination. It's latent heat being given back. Nature uses this trade-off constantly. Clouds form when warm, moist air rises and cools, causing water vapor to condense and release heat. This energy powers storms, fuels rainfall, and drives much of the planet's weather. On a smaller scale, we use the same principle every day without thinking about it. When you boil water in a kettle, the energy from the stove doesn't just raise the temperature, it also goes into pushing molecules apart until they burst free as steam. That's why the temperature plateaus once boiling begins. All the incoming heat is being converted into the energy of evaporation. The cloud rising from the spout carries away vast amounts of stored warmth, invisible until it touches something cooler and turns back into droplets. This interplay of heating, cooling, and transformation gives water its deep connection to comfort. It's why a warm bath feels steady rather than scalding. The water's high specific heat makes it resistant to sharp temperature shifts. It's why a cup of tea stays warm long after it's poured, slowly releasing the energy it's absorbed. And it's why walking through coastal fog can feel strangely mild, the air wrapped in moisture that buffers the extremes. Water's control over temperature also shapes entire climates. The world's oceans act as immense heat banks, absorbing warmth during the day and releasing it during the night or through colder seasons. This moderation keeps temperatures in check, preventing the wild swings that plague drier landscapes. Even the gentle breeze that moves inland on summer afternoons, the sea breeze, owes its existence to the difference in how land and sea store heat. As the land warms faster, air rises and cooler air from over the ocean rushes in to take its place. The planet's weather at its core is an elaborate conversation between sunlight, air, and water's remarkable capacity for heat. Hot springs, geysers, and volcanic pools offer another glimpse of water's thermal nature. Beneath the ground, heated water can hold energy for years, carrying warmth up from deep rocks and releasing it slowly at the surface. Ancient civilizations built entire cultures around these natural baths, long before they understood the physics behind them. The same phenomenon that calms the human body also stabilizes the planet itself, a shared rhythm of heating, holding, and releasing energy. Water's thermal behavior is also essential in cooking. Steaming vegetables, poaching eggs, brewing coffee, each relies on precise control of temperature. Steam, though invisible when it first leaves the pot, is one of the most efficient carriers of heat known. When it condenses on cooler food, it releases its hidden energy in an instant, cooking evenly without scorching. That's the same reason steam burns are more severe than burns from boiling water. The vapor gives back its latent heat all at once. Even everyday sights reveal this quiet physics. When you see a bathroom mirror fog after a shower, what you're looking at is the moment vapor surrenders its stored energy and turns back into liquid. Each tiny droplet forming on the glass has just given off a microscopic burst of warmth. A kettle's plume carries away energy from the water below, rising, cooling, and vanishing into the air. In a sense, every puff of steam and every bead of condensation is part of a slow exchange, a whisper of heat moving from one place to another. This ability to store and release warmth with patience and precision makes water one of the universe's most effective mediators of temperature. It smooths the peaks and valleys of heat, spreads energy evenly, and protects life from extremes. Without it, Earth would swing wildly between burning days and frozen nights. With it, the planet stays in balance, buffered by trillions of tons of calm, steady liquid. In the end, it's not just numbers or equations that make water remarkable. It's the way we experience it. The warmth of a cup between your hands, the mist on a mirror, the soft exhale of a kettle. Each is a small lesson in the physics of comfort. Water takes heat, holds it, moves it, and gives it back gently, like a caretaker tending an endless fire. It's the reason your breath fogs on a cold morning and the air feels soft after rain, a quiet reminder that behind every calm moment lies an ocean of energy waiting to rise and fall in perfect balance. Water is often called the universal solvent, and for good reason. Few substances can resist its ability to pull things apart at the molecular level. Salt, sugar, gases, minerals, all find themselves undone and rearranged by this simple liquid. The secret lies in water's polarity. Each molecule carries a slightly negative charge on its oxygen end and a slightly positive charge on its two hydrogens, creating a tiny electrical imbalance that makes it irresistibly interactive. When you drop ordinary table salt into water, that polarity goes to work instantly. Salt is made of sodium and chloride ions held together by strong electrostatic forces. In solid form, they cling to each other tightly, forming crystals. But when they meet water, something remarkable happens. The positive hydrogens in the water are attracted to the negatively charged chloride ions, while the negative oxygen ends face the positively charged sodium ions. One by one, the water molecules surround the ions, forming little cages known as hydration shells. Each ion becomes wrapped in layers of water, its former bonds to the crystal severed. The salt dissolves not by vanishing, but by being embraced, separated, and stabilized in a new kind of order. This same process explains why sugar melts away so easily in your tea, while oil stubbornly floats on top. Sugar molecules, though large, are studded with oxygen and hydrogen atoms that can form hydrogen bonds with water. Oil, on the other hand, is made mostly of long chains of carbon and hydrogen, which share electrons evenly and offer no charges for water to grab onto. To water molecules, oil is like a guest at a dance who refuses to hold hands. The two simply part ways, the water gathering with its own kind and the oil forming droplets above it. That refusal to mix gives rise to one of chemistry's quiet wonders, micelles. When certain molecules have both a water-loving end and a water-fearing end, such as soap, they arrange themselves into tiny spheres. The hydrophobic tails tuck inside, safe from water, while the hydrophilic heads face outward. These micelles trap oils and dirt within, allowing them to be rinsed away. It's one of nature's simplest and most elegant cleaning tricks, born entirely from the way water interacts with charge. But water's dissolving talents go even deeper. Even pure water isn't truly empty. Its own molecules occasionally break apart in a delicate balance known as self-ionization. At any given moment, a few molecules separate into a positively charged hydrogen ion, which in reality is a bare proton, and a negatively charged hydroxide ion. These ions exist in equal amounts, maintaining water's neutrality. The product of their concentrations is called Kw, the ionization constant of water. It's small, only about 10 to the power of -14 at room temperature, but it underpins the entire concept of pH. pH, short for potential of hydrogen, measures the concentration of hydrogen ions in a solution. A neutral solution like pure water has a pH of 7 because the hydrogen and hydroxide ions are perfectly balanced. When acids dissolve in water, they donate extra hydrogen ions, lowering the pH. When bases dissolve, they mop up those ions, raising it. This simple equilibrium governs the chemistry of oceans, blood, and soil alike, and though we often think of neutral water as inert, it's actually alive with tiny fluctuations, a quiet equilibrium that never stops shifting. Water also dissolves gases, a feature that keeps the planet breathing. Oxygen and carbon dioxide both slip into water molecules through weak interactions. Fish depend on dissolved oxygen, and plants in the sea release it again during photosynthesis. Temperature plays a crucial role. Cold water holds more gas than warm water. That's why mountain streams are so lively with bubbles, and why warm lakes can suffocate fish during heat waves. Every change in temperature alters the delicate balance between water and the air above it. Carbon dioxide is especially important. When it dissolves in water, it reacts to form carbonic acid, a mild but influential substance. This interaction links the chemistry of the atmosphere with that of the oceans. It is part of a global balancing act, carbon moving quietly between air, water, and rock. Without it, the planet's climate and geology would evolve in very different ways. Geology offers some of the most striking demonstrations of water's dissolving power. When rainwater, slightly enriched with carbon dioxide, seeps into the ground, it becomes a gentle acid capable of slowly eating away limestone. Over centuries, that process carves vast underground caverns and tunnels. Stalactites and stalagmites grow drop by drop as dissolved minerals are redeposited when the water evaporates. Each icicle-shaped formation is a frozen record of chemistry and motion, water dissolving, carrying and rebuilding stone with infinite patience. Mineral springs provide another example. As groundwater travels through layers of rock, it picks up trace elements, calcium, magnesium, iron, until it emerges at the surface, enriched and distinct in taste. Some waters bubble naturally with dissolved carbon dioxide, forming effervescent springs prized since ancient times. Civilizations have long treated these mineral waters as curative, not just for their warmth, but for their complex chemistry. What people once described as life in the water is, in scientific terms, the quiet work of dissolution and equilibrium. Even something as simple as taste reflects the chemistry of water. The purest distilled water, stripped of all ions and minerals, can taste strangely flat, almost empty. It quenches thirst but lacks character. Mineral-rich waters, by contrast, carry subtle notes depending on their contents. A hint of sweetness from calcium, a metallic edge from iron, a smooth softness from bicarbonate. Some cultures have turned this into ritual, celebrating the local differences as though water itself were a kind of wine. Each spring and river tells a geological story through its flavour. This variety also explains the difference in mouthfeel between different waters. Hard water rich in calcium and magnesium can feel heavier or slightly chalky, while soft water glides easily across the tongue. None of these traits make one kind better than another. They simply reveal water's astonishing sensitivity to the materials it encounters. Every pipe, rock, or cloud leaves its signature on the liquid that passes through. From a scientific standpoint, water's universality as a solvent lies in its ability to balance opposites. It can pull ionic compounds apart yet stabilize them in solution. It can host acids and bases at the same time, maintaining a dynamic equilibrium. It can dissolve gases, shape landscapes, and carry minerals across continents, all because of its simple polarity. Other liquids dissolve some things well, but few dissolve so much, so gently, and so dependably. It's worth pausing to consider how this behaviour touches daily life. From the fizz of a carbonated drink to the sparkle of a stalactite, from tea steeping in a cup to the formation of coral reefs, all depend on the same molecular skill. Water takes what is solid, separates it without violence, and makes it part of something larger. Perhaps that's what gives it its quiet elegance. It's not a force that smashes or burns. It persuades. It pulls molecules apart with patience and holds them safely within its embrace. In every glass, every ocean wave, and every drop of rain, that same balance plays out. Polarity meeting charge, chemistry meeting calm. Water dissolves the world not by destroying it, but by connecting it molecule to molecule until everything is part of a single flowing whole. Every landscape on Earth has been touched, shaped, or rewritten by water in motion. A single drop of rain may seem harmless, but multiplied across the sweep of a storm, it becomes a sculptor. It digs, smooths, and carries away. Over centuries, rivers and rain have carved mountains into valleys, ground rock into sand, and drawn intricate lines across continents. The Earth's surface in many ways is water's patient artwork. The story begins with rain. When clouds finally release their burden, each droplet falls with the energy of its descent, striking soil, rock, or leaf. Some soak in, some evaporate, and some begin to flow. At first, this movement is barely noticeable. A thin sheet of water spreading across the surface, following tiny irregularities in the ground. This sheet flow gathers strength as it moves downhill, and soon the water begins to organize itself. Small channels form. These merge into larger grooves known as gullies, which grow into the earliest forms of streams. As the water gathers, it carries with it small fragments of the land, grains of sand, bits of clay, specks of organic matter. Each raindrop that splashes against the ground loosens another particle, setting it free to travel. The steeper the slope, the faster the flow, and the more material it can carry. The process is simple but relentless. A hillside after a storm may look unchanged, but on the smallest scale it's been reshaped. Soil shifted, rocks smoothed, roots exposed. Over time, as streams merge and grow, they become rivers, the most expressive sculptors of all. Rivers don't carve in straight lines. They meander. Look at any aerial photograph of a floodplain, and you'll see the gentle curves, the loops and bends that mark a river's restless path. These meanders are not random. They're the natural outcome of flowing water meeting friction. Where the current moves fastest on the outer edge of a bend, it erodes the bank, cutting deeper into the land. On the inner edge, where the current slows, sediments settle out and form sandy point bars. The bend grows wider, drifting gradually downstream like a snake through grass. Given enough time, a meander can become so exaggerated that the river eventually cuts across its own loop, leaving behind a crescent-shaped lake called an oxbow. These isolated pools are the fingerprints of old rivers, reminders of how the water once turned and twisted before finding a shorter path. Each curve and cut-off tells a story of energy, friction, and balance. Rivers are always negotiating between gravity pulling them forward and the landscape trying to slow them down. The sediments rivers carry are their tools as well as their byproducts. Coarse gravel scrapes at the riverbed. Sand scours rock, and silt clouds the water like a painter's wash. But as the current slows, the river changes from sculptor to builder. Where it reaches flat ground, it begins to deposit the load it's carried, layer upon layer of fine material spread by currents and tides. This is how deltas are born. A delta forms where a river meets a standing body of water, such as a lake or the sea. As the flow slows abruptly, suspended sediments drop out, building up wedge-shaped plains that stretch outward over time. The Nile, the Mississippi, and the Ganges have all built vast, fertile deltas this way, landscapes both fragile and rich. Their soils are constantly renewed by fresh deposits, making them ideal for life, but vulnerable to change. Alluvial fans follow the same principle, but in drier places, where rivers flow from steep valleys onto flat plains. Instead of forming a wedge in water, the sediment spreads into a fan shape, glittering with pebbles and sand washed down from the mountains. In both forms, the hand of water is visible, drawing, erasing, and redrawing the land in slow motion. While rivers sculpt mechanically, they also shape the planet chemically. As water moves across rock, it dissolves minerals, carrying away invisible cargo. Carbonate rocks like limestone are especially susceptible. Rainwater, slightly acidic from dissolved carbon dioxide, reacts with calcium carbonate, slowly eating away the stone. Over thousands of years, this process hollows out caverns and sinkholes, leaving behind underground labyrinths of stalactites and stalagmites. Each drop that falls from a cave ceiling contains a trace of the dissolved rock above, which it redeposits as it drips and evaporates. In this way, water can both destroy and create, dissolving mountains while building delicate mineral cathedrals below. This same chemistry continues in every stream. Silicate minerals break down into clays, releasing ions that plants later use as nutrients. Tiny traces of dissolved salts flow to the ocean, where they accumulate over millions of years, giving seawater its familiar brine. A glass of seawater today holds molecules that have been recycled through countless rivers, rains, and rocks, a mineral memory of the continents themselves. Even the colour of a river tells a story of its chemistry. A milky turquoise stream in the Alps owes its hue to rock flower ground fine by glaciers. A reddish-brown current in the tropics carries iron-rich sediments from ancient soils. A green, slow-moving river may be alive with algae nourished by the minerals it transports. The palette of flowing water is as varied as the materials it wears away. For all its strength, water also knows restraint. In some seasons, rivers rest, shrinking to thin threads between exposed stones. In others, they wake violently, swelling with floodwater, spilling across their banks and leaving behind new layers of silt when they retreat. Each flood renews the floodplain, replenishing soil fertility, smoothing the river's curves, and reminding everything nearby who truly shapes the land. Civilizations have flourished and fallen by these cycles, timing harvests and rituals to the rhythm of the river's rise and fall. There's a quiet balance in this process: erosion and deposition, loss and renewal. The Himalayas crumble grain by grain, feeding deltas thousands of kilometers away. A particle of dust on a mountain slope may one day settle in an estuary or drift into the sea to become part of the next generation of rocks. Through it all, water remains the courier, endlessly moving matter from place to place, patient and impartial. On a smaller scale, rain continues the work of shaping and nourishing. Each storm rejuvenates the surface of the land. Raindrops compact soil here, loosen it there, wash nutrients into roots, and carve minor channels that will one day grow into streams. The scent of rain on dry earth, called petrichor, comes from oils and compounds released when drops strike the ground. It's the smell of chemistry and renewal, the planet's quiet sigh of relief. If you listen closely, you can hear the language of rain, a steady patter on leaves, a soft drumming on rooftops, a distant roar as it gathers into runoff. All are voices of the same process. The sound of rainfall is the signature of replenishment, each drop part of an endless cycle of erosion, transport, and rebirth. Rivers and rain have been sculpting earth for billions of years, wearing down the old and laying the foundations for the new. When the storm ends and the world falls silent again, you can almost feel the surface of the planet exhale. A thin film of water sinking into the soil, a renewed gleam on every stone, the faint hush of movement continuing underground. What began as raindrops becomes rivers. What rivers carve becomes continents, and what they carry away will one day rise again as mountains. The water never stops working, never stops moving, and never forgets the shape of the world it made. High in the world's coldest regions, where snow rarely melts and the air holds more silence than sound, the slowest rivers on earth begin to take shape. Each winter adds another thin layer of snow, fragile at first, then compacted by the weight of the years above it. What starts as soft crystals soon becomes something denser and more determined. Firn, the halfway state between snow and ice. Grain by grain, air is squeezed out. The crystals fuse together, and over decades the mass transforms into glacial ice, dense, heavy, and alive with movement. Though it seems frozen and still, a glacier is never truly motionless. It flows, inching forward under its own immense weight. At the surface, brittle ice cracks and folds. But deep below, the pressure turns it plastic, capable of bending and stretching without breaking. This process, called plastic flow, allows glaciers to creep downhill like thick syrup, following valleys carved long ago by water. Beneath the ice, another kind of motion takes place: basal sliding. Meltwater trapped between rock and ice acts as a lubricant, letting the glacier glide over its bed with quiet persistence. Together, these movements let something seemingly solid behave like a liquid, advancing a few centimeters to several meters each day, depending on slope and temperature. Over centuries, glaciers sculpt entire landscapes. They carve deep U-shaped valleys where once narrow rivers ran. The difference is striking. River valleys tend to form steep-sided V-shapes, but glaciers, with their immense weight, scrape and grind the walls and floor evenly, leaving behind broad troughs that open toward the sea. At the valley heads, glaciers gouge out amphitheatre-like hollows called cirques, the birthplaces of glaciers, where snow first gathers and turns to ice. High ridges between neighbouring glaciers are sharpened into arêtes, and where several cirques meet, their peaks are carved into knife-like spires called horns. The famous Matterhorn in the Alps is one of these, sculpted by ice into its perfect pyramid shape. As glaciers advance, they act like slow-moving bulldozers, pushing rocks and debris before them. When they retreat, they leave behind mounds of this material known as moraines. Some form at the sides, others at the snout, and still others mark ancient stages of retreat, like footprints of the glacier's long journey. Beneath the ice, as the glacier moulds the land, it leaves behind drumlins, elongated hills shaped like teardrops pointing in the direction of the ice's flow. Each landform tells part of the same quiet story, the relentless patience of frozen movement. Inside a glacier, beauty hides in its colour. Pure glacial ice isn't white, but a deep, luminous blue. The reason lies in the way ice interacts with light. When sunlight enters the ice, the red and yellow wavelengths are absorbed, leaving behind the shorter blue wavelengths that scatter back to our eyes. The thicker the ice, the more pronounced the colour becomes. A thin crust of snow glows pale and milky, but deep crevasses and ice caves shine with an otherworldly turquoise, like frozen oceans turned solid. Those crevasses, long cracks in the glacier's surface, are both dangerous and magnificent. They form where the ice stretches as it moves over uneven ground, opening deep fissures that can reach tens of meters down. From above, they appear as jagged blue scars tracing the stress lines of the glacier's slow advance. In places where the glacier flows over steep drops or obstacles, the surface fractures into towering blocks called seracs. These frozen pillars can rise taller than buildings, constantly shifting as gravity and meltwater tug at their foundations. Seen in the pale light of dawn, a field of seracs looks like a cathedral built from blue glass, every wall and spire carved by time rather than hand. Beneath the ice, another kind of artistry unfolds. As glaciers grind against bedrock, they act like giant sheets of sandpaper, pulverizing rock into an ultra-fine powder known as rock flour. This powder is carried away by meltwater streams, colouring the water an opaque milky turquoise. The famous glacial lakes of the Alps and the Canadian Rockies owe their surreal hues to this mineral dust suspended in their depths. Each summer, as meltwater flows stronger, the lakes brighten. In winter, when the glaciers retreat, they fade to a calmer tone. Nature repaints these colours anew each year, one melt season at a time. The erosion beneath glaciers shapes not just valleys, but entire mountain ranges. As the ice grinds forward, it scours away loose rock, smoothing hard surfaces and carving striations that reveal the direction of movement. When the glacier finally melts, it leaves behind a transformed landscape, polished stones that catch the light, boulder-strewn plains, and basins that fill with meltwater to become new lakes. In the quiet aftermath, plants creep back into the soil, and the long cycle of erosion and renewal continues. 2. Humans. Glaciers may seem eternal, but their lives are measured in slow, deliberate rhythms. They grow in times of heavy snowfall and shrink during warmer periods, advancing and retreating with the patience of ages. Some expand for thousands of years before withdrawing. Others surge forward rapidly only to fall still again. Scientists studying ice cores drilled from ancient glaciers can read these movements in the layers, thin bands of compressed snow that preserve tiny bubbles of trapped air. Within them lie records of past atmospheres, volcanic eruptions, and even changes in sunlight from centuries ago. A glacier in that sense is not only a sculptor, but also an archivist, storing the memory of the world in frozen form. Even the sound of a glacier reveals its hidden vitality. Beneath the apparent stillness, ice groans, pops, and sighs as it shifts and settles. Cracks echo through the valley, followed by silence so complete it seems to hum. Each sound marks a tiny rearrangement, a fracture forming, a piece falling, a hidden stream carving a new tunnel beneath the ice. To stand near one is to feel time stretched thin, seconds marked by the slow pulse of centuries. Every glacier carries its own signature, its flow rate, its debris, its colour, but all share the same patient purpose. They grind mountains down and build valleys up, ferry minerals to the sea, and feed rivers that sustain life far below. They work invisibly, reshaping continents 1 millimeter at a time. At the end of their journey, glaciers return what they borrowed. The ice melts into rivers that sparkle with fine silt, feeding forests and wetlands far downstream. The particles of rock once trapped beneath the ice become the fertile ground for future growth. In this way, the glacier's work never truly ends. It simply changes form, continuing the endless cycle of creation and renewal. If you were to pause in that frozen world, the air sharp, the snow muffled, you might notice the smallest movement, a crack spreading, a low rumble echoing through the valley. In that single sound lies the glacier's heartbeat, measured not in seconds, but in centuries. Each shift, each sigh is part of a story written slowly, patiently across the face of the earth. The ocean is vast beyond imagination, a single continuous body that wraps around the world and hides most of its secrets beneath a moving skin of blue. From the shore it looks simple, a sheet of water rising and falling in slow rhythm. But beneath the surface the sea is layered, structured, and alive with invisible motion. The deeper you go, the stranger it becomes. Light fades, temperature drops, and sound begins to travel farther than sight. At the top lies the surface mixed layer, stirred constantly by winds, waves, and currents. It's the ocean most people know, warm, sunlit, and full of life. Here, sunlight can penetrate to a depth of about 200 meters, though it weakens with every passing meter. The upper waters are churned and blended daily, making them uniform in temperature and composition. Below that warmth lies a narrow, mysterious boundary called the thermocline. In this zone, temperature plunges rapidly. A few hundred meters can mean a drop of 10 degrees or more. The water above is buoyant and active. Below it, the cold abyss begins. Past the thermocline lies the deep ocean, sometimes called the abyssal plain. Here, light vanishes entirely, and temperatures hover just above freezing. Pressure builds to crushing levels, yet the water moves with astonishing calm, flowing slowly through vast underwater valleys and ridges. It's a realm where light can't reach, but sound can. In fact, sound travels farther and faster underwater than in air. Whales rely on it to communicate across hundreds of kilometers, their calls bending through layers of different density. Submarines use it to map the seafloor, tracing echoes through the dark. Even the faint hum of distant waves can be heard deep below, transformed into soft vibrations that ripple through the deep like the ocean's own whisper. The layering of the sea isn't just a matter of temperature, it's shaped by salinity too. Saltier water is denser than fresh water, and when differences in salt content meet differences in temperature, they create subtle bands of stratification. In polar regions, cold water sinks to great depths, while in the tropics, evaporation leaves surface layers dense and heavy. The ocean is always balancing itself, mixing and separating, endlessly adjusting its density like an enormous breathing organism. These small shifts drive some of the planet's largest currents, linking surface winds to the deep, slow circulation that redistributes heat around the world. Near the surface, this invisible structure becomes visible through motion, waves, swells, and the faint patterns they leave behind. A wave is simply energy moving through water, not the water itself moving forward. The molecules rise and fall in place, tracing circles as the energy passes. Most waves are born far away, stirred by winds over open seas. They travel for thousands of kilometers, organizing themselves into swells, smooth, rolling humps of energy that arrive at distant shores long after the storm that made them has faded. Standing at the edge of the sea, you can feel those swells as a steady rhythm beneath the chaotic splash of smaller waves. The ocean's heartbeat slow and patient. There are also waves hidden below the surface, internal waves that ripple along the boundaries between layers of different density. They can rise hundreds of meters tall, yet remain invisible from above. Satellites sometimes detect their faint signatures, lines and curves where the surface water subtly shifts in color or texture. Beneath the calm, these giant slow waves roll endlessly through the dark, mixing nutrients and shaping the ocean's internal weather. The constant motion doesn't stop with waves. Twice each day, the entire sea responds to a larger rhythm, the tides. These slow surges are caused by the gravitational pull of the moon, assisted by the sun. As the Earth turns, the oceans bulge slightly on the side facing the moon, and again on the opposite side, creating 2 high tides and 2 low tides every day. The timing varies with coastlines and geography, but the principle remains universal. Gravity pulling water into rhythm with the cosmos. Tides are the planet's metronome, setting a tempo that has guided life for billions of years. Shorebirds feed by it, mangroves grow according to it, and even ancient human settlements built calendars around its predictability. To watch a full tidal cycle is to see the earth breathe, the slow inhale of rising water, the long exhale of retreat. Every grain of sand, every pool of tide water participates in that motion. You can almost sense the connection between the moon's silent orbit and the shifting foam around your feet. The rhythm of tides is so steady that time itself seems to bend around it. At night, the sea reveals yet another layer of magic. In many parts of the world, the water glows when disturbed, the light of living organisms known as bioluminescence. Tiny plankton called dinoflagellates produce flashes of blue-green light when jostled by waves or movement. Each one is smaller than a pinhead, but when billions gather, their light can outline every ripple and swirl. A breaking wave becomes a band of stars. A boat's wake leaves a glowing trail like liquid fire. Even the footprints of someone walking along the shore can shine for a moment before fading back into darkness. Bioluminescence is chemistry turned into wonder. The light comes from a reaction between a molecule called luciferin and an enzyme called luciferase, releasing photons instead of heat. It's used by organisms for defense, communication, or simple camouflage. Some deep-sea creatures use it to lure prey, while others flash in patterns to attract mates. But to the human eye, it feels like pure enchantment. The sea whispering back with light instead of sound. Beneath this beauty lies a balance as precise as any clock. Every current, wave and tide plays a role in distributing energy and nutrients. The surface layers feed on sunlight, supporting blooms of plankton that form the base of the food chain. As these organisms die, they sink, carrying carbon into the depth where it's stored for centuries. The ocean, in that sense, is both mirror and memory, reflecting sunlight while quietly regulating the planet's temperature and chemistry. The ocean's whisper is never quite silent. Even in the calmest moment, it speaks through motion, the faint hiss of receding foam, the low rumble of distant surf, the hum of water against rock. Stand by the shore on a still night, and you can hear it breathe. The air tastes faintly of salt. The horizon shimmers under the moon, and the water stretches beyond sight or comprehension. Beneath your feet, tides are shifting, currents turning, and creatures glowing unseen in the dark. All the layers of the sea, warm, cold, bright, and black, are connected by these quiet rhythms. The waves you see began as wind half a world away. The deep currents below you may not surface again for 1,000 years, and the same moon that pulls the tides above the shore stirs the water miles beneath. The ocean is a whisper that never ends, a voice shaped by gravity, chemistry, and light, speaking softly to every shore it touches. The sky may look empty, but it's filled with motion, an invisible cycle of water rising, cooling, and falling again. Every cloud, every wisp of mist, every droplet on a window begins with a simple act of escape. When sunlight warms oceans, rivers, or even a damp field, water molecules near the surface gain enough energy to break free and drift upward as vapor. They are weightless for a moment, part of the unseen breath of the planet. Yet, as they rise, the air cools and expands, and their freedom fades. What was once invisible begins to gather again, tiny droplets forming in the air, each one clinging to something even smaller. For a cloud to exist, vapor alone isn't enough. Water needs a surface to condense on, something to hold on to. The atmosphere provides countless such surfaces in the form of microscopic particles known as condensation nuclei. Dust, pollen, sea salt, smoke, even fragments of volcanic ash. Water vapor condenses around these motes, creating droplets so small that 1,000 of them could fit across the width of a single hair. Millions of these droplets cluster together, scattering sunlight and giving clouds their familiar softness. Once formed, these droplets continue to grow. Some collide and merge, a process called coalescence, while others freeze into tiny ice crystals if the air is cold enough. As they fall and rise within the turbulent air currents of a cloud, they exchange moisture, gain mass, and eventually become heavy enough to overcome the pull of the updrafts holding them aloft. That's when rain begins, not as a single event, but as the collective decision of countless droplets that have finally grown too heavy to stay airborne. Clouds come in families, each one shaped by altitude, temperature, and the moods of the atmosphere. The lowest are the stratus clouds, flat grey blankets that stretch across the sky, muting sunlight into a soft, even glow. They bring calm weather or light drizzle, their movements slow and measured. Higher up, cumulus clouds rise in billows and towers sculpted by convection. They form when warm air from the ground rises and cools, building those bright cotton-like shapes that drift through fair weather, or when energized grow into towering cumulonimbus clouds that unleash thunder and lightning. Higher still, where the air is thin and cold, wispy cirrus clouds streak the sky like brush strokes of white paint. Made almost entirely of ice crystals, they glow faintly in the sunlight and often herald a change in weather. Together, these cloud types form a layered tapestry, each telling a story about the state of the air. Meteorologists can read those stories like a script, knowing, for example, that a lowering ceiling of stratus means approaching rain, or that cirrus trails spreading out from the west often signal a coming storm. The atmosphere doesn't reserve its artistry for clouds alone. Sometimes the same process of condensation happens close to the ground, and the result is fog, a cloud that decided not to rise. Fog forms in several ways depending on how the air cools. On calm, clear nights, the ground radiates heat into space, cooling the air just above it until water vapor condenses into droplets. This is radiation fog, the kind that settles in valleys and fields before dawn, wrapping the world in silence. Along coastlines, warm, moist air moving over a cooler surface creates advection fog, the rolling kind that drifts inland like soft smoke. And when air climbs a slope, cooling as it rises, it can form upslope fog, clinging to hillsides in long ribbons that stretch across the landscape. Even when fog doesn't form, the same cooling can create dew or frost, miniature weather events you can touch. On cool mornings, you can see dew collecting along grass blades, window panes, or spider webs. Tiny beads born from the same process that makes clouds. When the temperature dips below freezing, those droplets crystallize into frost, painting the world in fragile lace. Dew and frost are in essence doorstep meteorology, a reminder that the same physics guiding thunderheads and storms also happens quietly in your garden. Not all rainfall is equal, and understanding their origins reveals just how many stories a single molecule of water can tell. A gentle drizzle forms from small uniform droplets falling through stable air. The drops are light, barely disturbing the surface they land on, more like a soft brushing than a fall. Drizzle tends to come from low stratus clouds where updrafts are weak and the droplets never grow large. A sudden shower, on the other hand, is born in tall cumulus towers where powerful convection hurls droplets upward to collide and merge before they tumble earthward. These raindrops are much larger, their paths turbulent, their impact audible. Yet whether in drizzle or downpour, the molecule itself hasn't changed. Only the journey it took through air currents and temperature gradients. The next time you feel rain on your skin or watch fog settle into a valley at dawn, remember that you're witnessing the same ancient dance that began in the hearts of stars and shaped every ocean, river, and cloud. Each droplet carries with it a story written across billions of years, a quiet journey from the void of space to the warmth of your hand. Water has sculpted mountains, cradled life, and whispered through every moment of Earth's long history, and it continues still, patient and endless, moving through the world with a grace that asks for nothing but to be noticed. Sleep peacefully.